I would like to welcome you all here. My name is Wolf Geppert. I'm the chair of the European Astrobiology Institute, and it's my pleasure to present a colleague whom I will be have been knowing for quite a long time as a seminar speaker today. Paola Caselli did her PhD at the University of Bologna, which is also one of my cooperation partners, and then for some time joined Eric Herbst at the Ohio State University, and also worked 2 years at the Smithsonian Center in Harvard for astrophysics. And in 1996, she became a researcher at the Italian Arcetri Astrophysical Observatory close to Florence. And after that, she was visiting scholar at the Department of Astronomy at Harvard University. And in 2007, she became professor of astronomy at the School of Physics and Astronomy at the University of Leeds, where there is one of the leaders of our project teams now. In 2014, she became the director of the Center for Astrochemical Studies at the Max Planck Institute for Extraterrestrial Physics, located in Garching, northeast of Vienna. And I will finish now and leave the floor to Paola. Welcome again, welcome to you all. And Paola, the floor is yours.
Thank you very much, Wolf, and thank you all for joining. Yeah, it's great to see colleagues and friends also from across the ocean. Yeah, I kind of feel that I would like to meet you all in person at this moment, but now let me share the screen and let me start. So here, and I start with my talk, which is about our astrochemical origins. So I guess, as all of you already know very well, all of us have been formed from molecular clouds. This is an example that you see here in front of you at the moment. It's the Taurus molecular cloud seen in the optical. And you can see here lots of stars in the background. Many of the stars, if not all of them, have actually planets. But what we are interested now is really to look at these dark regions. Dark because these regions absorb the light from the background stars, in fact, because they contain dust, as we will see, that absorb this light. But the other thing that you may not notice at the first sight is that if you go a little bit closer, you start to see some kind of red filamentary structure, some kind of emissions, and these are sites of formations of stars. They are forming right now. So stars, as well as planets, are forming in these molecular clouds. So all the ingredients to form stars, to form planets, to form life are actually contained in these clouds. So we really wanted to understand their composition, how the molecules form there, and how they evolve from clouds to structures that are much more sophisticated, like living beings. Of course, I'm not going into the formational origins of life. Of course, I'm very interested into that, but as an astronomer, I'm mostly focusing on these early phases. So I will just start with some motivation slides and then go into the talk. So you have to think that as of September 2021, so there is a total of 241 molecules that have been discovered in space. And you can see all of them with detailed description in this very nice, actually, live paper from Brett McGuire in 2021 that he is updating all the time. And so most of these molecules are actually organic. This is, of course, we know because it must be like that, because we know how rich is the chemistry of carbon. And you can see in this table that there are actually quite complex organics, and some of them, for example, this aminoacetonitrile that was discovered in 2008 toward a molecular cloud called the Sagittarius B2, close to the galactic center of our galactic center. It's just one step away from glycine, which is, as you know, the simplest amino acid. Now, if we actually go much more recent literature, I can find this nice paper by Victor Revilla and collaborators from Madrid, the Center for Astrobiology in Madrid, and they just discovered last year, this is a paper that has been published in the proceeding of the National Academy of Sciences, they detected the ethanolamine. Ethanolamine is actually the simplest phospholipid head group, and here it is shown as it is typically found in cell membranes. Okay, so this is of course the only part that has been detected in space, but this is just to let you understand how far we are going in complexity in these regions. And if this is not enough, when we look at the primitive material in our solar system, for example, the so-called carbonaceous chondrites, these are among the most primitive rocks that have been formed during the formation of the star and planet, our sun and planets. So these are 4.5 billion years old, and you can see here that inside some of these material, especially in this dark matrix that is filled with organic molecules, you can find all kinds of prebiotic molecules. For example, more than 200 amino acids were found in the Murchison meteorite, and these are building blocks of proteins. But this is not the whole thing. There are also fatty acids there. There are nucleobases. So nucleobases are the building blocks of our genetic code. So basically everything that you need to form, and even more, because we don't need the 200 amino acids, we are going along with 20. So even more than what we need to make living beings are actually made, present, even before planets are forming, which is astonishing. I mean, really beautiful. This is one, in fact, of the motivation of my interest in this field. And then, of course, you can look at theoretical papers. This is the work done by peers and collaborators. Here there is also contribution from Heidelberg group, from Thomas Henning, where they actually consider these early phases of our planet, the Earth, and look into the contribution from, say, volatile material from meteoritic bodies and also comets, and look at the processes that go on during the early phases of evolution of our planet. So what they found is that starting from these volatile and prebiotic molecules that I show you just one slide away, to make RNA polymers, so ribonucleic acid polymers, you just need a little bit of time, which is about what they found is about 200 million years after the moon forming impact. So about 4.2 billion years ago, in their models, they have RNA. So they're saying that the formation of life takes place in a really short time after the formation of a planet. And you can think that this seeding must be some kind of universal seeding, because as we will see, we see these complex organics everywhere we look, okay? So now just a little bit of advertisement. This is the Origins Excellence Cluster that is in the Munich area. You can see here beautiful Munich with the Alps. And many people are actually involved in trying to arrive at these early stages of to understand the origins of life. So my talk, we will go through relatively quickly into the dark clouds and prestellar cores. These are the really the units within which stars and planets form. And this is one of my most, in the past decades, I have been working a lot on these prestellar cores. These are regions within molecular clouds where stars and planets form. I will also talk a little bit about the importance of cosmic rays. Cosmic rays are these energetic particles that are accelerated by supernovae and other shock events that they permeate across the whole galaxy. So they are everywhere and they interact a lot with material, even in dense regions like dense clouds, but also protoplanetary disk. We will also talk about complex organic molecules, and I will sometimes use this acronym COM or COMS for complex organic molecules. I remember that as astronomers consider complex already molecules with more than 6 atoms, so already a molecule with 6 atoms inside is for us complex. And finally, I will go toward the more evolved stages and toward then our solar system and stellar systems like our own. So let me start with the Milky Way. This is our Milky Way, our galaxy, our home, as seen in the optical. And you can see again, as I show you in the first slide, you see this nice background of stars. That here is the galactic center, very bright, is a bulge, and what we are interested in are these dark regions, these dark lanes that are about 10 Kelvin in temperature, so very cold, are almost, vacuum in terms of density, high vacuum, because the average density is about 1,000 H2 molecules per cubic centimeter. Probably even less in some region, but the molecular clouds, let's say they're 1,000 H2 molecules per cubic centimeter or larger. And H2, of course, is the most abundant molecule that is there, but it's not easy to detect. So if we actually, instead of having a telescope that is focused, or say an optical telescope, we use an antenna, not even a big one. In fact, the map that I'm going to show you was made with the 1 meter antenna. You see that where it was dark, it is now very bright. And this is due to the fact that where there are these dark lanes where material is screened from the interstellar radiation field, you have molecules that start to form and thrive. And so this is the beautiful map that was done in 2001 by Dame, Hartman, and Thaddeus using 2 telescopes, one at Harvard Smithsonian Center for Astrophysics and one in the South Hemisphere, looking at the second most abundant molecule in the universe, carbon monoxide, second, but still this is say the most easily detected molecule in the universe, okay? And you can see, just going back and forth, that there is a great match between the darkness in the optical and the brightness in the millimeter wavelength. So if you wanted to study a dark cloud, you have to zoom in a bit. So you have to have a little bit larger telescope. And for example, in this case, we are looking at the dark cloud, molecular cloud, but not in CO. Now it's seen in dust continuum emission with the Herschel satellite. And the dust continuum emission, when I talk about dust, I talk about dust grains that are, of course, part of these regions. The gas to dust mass ratio is 100, so it's a minor component of these clouds, but it's super important because, first of all, they absorb UV lights, so interstellar radiation field, so they can allow actually these molecules to form. And also, as we will see, these surfaces of interstellar dust grains act as catalytic surfaces where you can make quite interesting and complex organic molecules. Zooming in even more, we arrive at these prestellar cores. So prestellar cores are dense portion of molecular clouds where actually stars are not yet formed, but are in the process of forming, because we see, for example, evidence of contraction motions. And we notice that there is a very compact central region in the center of this prestellar core, which is seen, for example, in millimeter dust continuum emission, which can be detected and studied very well with deuterated molecules. I'm not going into this specific theme today, but just to tell you that with astrochemistry, we can actually find out which molecule to use to study certain specific parts of clouds and regions in the interstellar medium. So one thing that we understood already in 2007 with Antonio Crapsi, we used the VLA and observed the ammonia. Ammonia is very abundant in these regions. And with the interferometer, we could actually measure the temperature. This is the best thermometer we have for space. And we found that if you go toward the center of this cloud, so this is the distance from the dust peak of this prestellar core, the temperature goes down to about 6 Kelvin and goes up to about, say, 9–10 Kelvin in the outer part of the core. And this is consistent with our understanding of radiative transfer. So if you just have external heating from the interstellar radiation field and you take into account the attenuation of this radiation field, you can reproduce this. And this, in fact, was the theoretical curve. So what we found in this region is that because of this very low temperature of the core, molecules like, for example, CO, can freeze out. And in 1999, we measured that more than 90% of CO is actually frozen onto the surface of these tiny little dust grains in the central 7,000 astronomical units of this object. Now, astronomical units is the distance between, say, the sun and the Earth, and is 150 million kilometers, just for those of you who are not astronomers. So this is what happened. We have our silicates or carbonaceous materials surrounded by thick icy mantles, rich in water, CO, and other molecules. More recently, this is the paper that I hope to receive soon. The final referee report is about the new ALMA observations of the same prestellar core, where we actually measured deuterated ammonia. As I told you, deuterated molecules are really become very abundant toward the center of this region. And what we detected with the ammonia is a very flattened structure, which is probably the precursor of the protoplanetary disk. But most importantly, with our model, chemical models and radiative transfer, we could reproduce very well the lines that we detected with ALMA using non-LTE, so non-local thermodynamic equilibrium radiative transfer modeling. And you can see here that our model, the red curve here, the red histogram, matches very well the data starting from the center and going away from the center by 2.5 arc seconds, which is our beam. And this has been reproduced considering that you have this freeze out of molecule. And this is our deuterated ammonia that goes down very sharply in the central, now 2,000 astronomical units. And this is the total depletion factor. The total depletion factor, so all the species heavier than helium reach values. So the total depletion factor is the sum of all the species heavier than helium in the gas phase and in the solid, divided by all the species in the gas phase. So it tells you how much it is actually in the solids. And you can see that toward the center, this factor becomes 10 to the 4. So in practice, this means that now we have a demonstration that is 99.99% that all species heavier than helium are actually frozen in the central 2,000 astronomical units of a prestellar core. So This is my view of dust grains in the center of this prestellar quartz. We are talking about sub-micrometer size particles that are like little snowballs completely covered by several hundreds of monolayers of ice. Some of these ice, most of these ice actually, especially in the region where you started to have the CO freeze out, will be very rich in CO, but then also will become rich with nitrogen, deuterated species, more and more going toward the center. And in fact, if we look at the previous work, this is laboratory work and studies by Burke and Brown in 2010, and they actually show that indeed the chemistry in this ice is very rich. It's very rich because it's not that they are isolated there and nothing can go there. You have the cosmic rays that are these, as I said, energetic particles that can bombard. Cosmic rays, basically, they don't care about these regions being dark and dense. They just go through and pass through the cloud without being disturbed at all. So they can actually inject energy in these ices. They can dissociate molecules, they can activate chemistry, and even say, for example, break bonds and allow more complex organics to form. For example, another important point to have these cosmic rays, without those we couldn't understand this observation, was our detection of water in the gas phase, done thanks to the high sensitivity of Herschel satellite that was done in 2012. This is the line that we observe. As you see, is a kind of complex profile. So we have emission in the blue side, so at say low velocity, and absorption in the red side, so at high velocity. And this can be reproduced if we are seeing the very central region of the core, which is in fact contracting in the process of formation of the star and the protoplanetary disk. So the main messages here, in fact, with this beautiful Herschel data, we could measure not just this infall and tell that the infall is proceeding very gently and very slowly. We call it, in astrophysical terms, subsonic, as it is written here. And so things are not very violent at all at the beginning, okay? So they're just going down very quickly, very gently. You have to think of these icy dust grains raining down like hails, you know, in the central region where the future star and planets will form. The total mass of this water vapor was measured to be, thanks to this line and our radiative transfer work, 0.5 Earth masses, and then from here we deduce a total mass of water ice of about 3 Jupiter masses. So we start already, even before forming the protoplanetary disk, we start already with a lot of water. And we need cosmic rays because cosmic rays are the ones who can photoabsorb, actually, because the cosmic rays mostly hit H2 molecules that then are excited in their upper energy level, then they fluoresce back, producing this very tenuous UV field that is then can actually photoabsorb some of the molecules in these ices. And this is a kind of a 3D view of what happens. So assuming now that we are zooming in on top of one of these dust grains, you have here your silicates or carbonaceous material, and here you have a cosmic ray proton that is intercepting a dust grain, and you can see what happens here, assuming that all this ice is actually pure water, which doesn't exist, but assuming that it's pure water, you have here, for example, the production of secondary electrons that can actually excite species. Also, you can have the breaking of bonds and forming, instead of water, you have OH, and then production of new molecules. And in fact, this is a very active field. We have work also going on at MPE and collaborators in Europe about what is the effect of these cosmic rays in ices. So we look at this flame track here and look at the chemistry that is produced. Also, Chris Schindler-Decker, who was a student of Eric Herbst, and then came to MPE as a Humboldt Fellow, he studied this, wanted to reproduce with the simulations the some of the work that was done in the lab, like in this case, for example, propagation of protons into O2 ice. And very interestingly, the work that Chris did with Eric Herbst was actually to find that if one does not take into account at all cosmic rays, it's very hard to reproduce some of the observed abundances with respect to H2 molecules of complex organic molecules like this HCO, CH3, which is quite ubiquitous. So you can see the difference in abundance as a function of time without cosmic rays and with cosmic rays, what Chris called radiation chemistry, okay? An interesting thing that then we did together when he was at MPE is to study the sulfur chemistry actually on in these ices, taking into account of this radiation from cosmic rays. And what Chris found is that the cosmic rays can transform the sulfur from being mostly in the gas phase and say H2 ice in the solid form in refractory allotropes. So these are the chains of sulfur, pure sulfur, that end up with this stable S8 molecule that is depicted here, and I'm sure you have seen it. If you go near volcanoes, you see these yellow stones, and this is S8. So the interesting thing is that these allotropes have part of those. I mean, not the whole chain. The S8 cannot be detected, but in, for example, with millimeter astronomy, but S2, S3, and S4 were detected in comet 67P, so in the Churyumov-Gerasimenko say comet that was visited by Rosetta, which is an interesting result because the sulfur chemistry is really one of these big question marks that we have as astrochemists. So let me move into complex organic molecules. We have known complex organic molecules since many, many years, and mostly they were detected at our active star-forming regions, and people very often were claiming, and I think even now they're claiming that all these molecules come from the evaporation of ices nearby. For example, high mass star-forming region or even low mass star-forming region. You can see here an example. This is another beautiful picture coming from the legacy of Herschel, from the Hexos team led by Ted Bergin, and you can see this is the Orion spectrum. You see a lot of, say, important organic and also prebiotic molecules. However, the interesting thing is that these complex organics are also found in cold regions. We know that since also many years, but I think it's more recently that we understand where these complex organic come from. And now also thanks to ALMA, for example, these are beautiful ALMA images of the pre-stellar core where we show the dense core here, mostly traced by the deuterated ammonia. And then here, the methanol. You see the methanol, which is the simplest, one of the simplest complex organic molecules, so simplest COM, is on one side and surrounds with the tenuous halo the whole core. So we now understand that these molecules can form like methanol, but many others, as you can see here. I put some of the literature that is very active field at the moment. Many complex organics are surrounding these cold objects, and we understand that they start to form as soon as you have the CO freezing out on the surface. This, of course, allows CO to be hydrogenated and forming methanol. This is the end point, the saturation point for the CO. And if you have a CO-rich surface, part of these formed molecules can actually be ejected more efficiently. So all this work has been described in this work here. So I think we understand some details, at least, of the main processes, the basic processes of the first formation of these complex organic molecules that happen in these cold regions upon CO freeze out. Okay, so now if we move on to say the formation of the central protostar and protoplanetary disk, what does it happen? Well, first of all, things are not dark anymore. Even if you look in the optical, you can actually look at this picture here that shows a dark core that was a prestellar core, and now you see a little plume here. This plume is actually part of the energetic winds that are produced and driven by these early phases of so this very young stellar object. And if you have an infrared telescope, like for example the Spitzer's telescope, then you can see very well inside the cloud. And now you see the lobes of this outflow, the central part here. And then you can imagine in the regions where the dust has been heated up and where you had a lot of, say, energetic processes, for example, shocks and outflow, as I listed here, you can actually release at least part of these ices, or totally if they are really very close to the protostar. So you start to have this very rich, say, chemically rich regions that are called hot cores for massive star-forming region, or hot corinos for low mass. And an example is this class 0 source. Class 0 means really young stellar object that just started to form, just switched on. And when we say just, we talk about times that are less than 100,000 years. You know, we are astronomers, so it's for us 100,000 years here is very short time. So this is a work by Jess Jorgensen and collaborators. They use ALMA to look at these complex organics into toward this young stellar object that is the IRA 16293, relatively nearby object. And they plot here, this is the work by Drozdoskaya and collaborators in 2019, they plot the fractional abundance of this complex organic as a divided by the abundance of methanol as a function of this abundance, same fractional abundance found in the comet 67P, okay? So you can see that the correlation is astonishingly good. So in the paper that it's very nice and I would like you to read, they actually claim, and I put the disclaimer here, the volatile composition of cometesimal and planetesimal is partly inherited from the pre and protostellar phases of evolution. Because of this very nice correlation, it's tempting to say that some of this material that now we see in the gas phase, because it has been heated up, it has been actually deposited into these primordial rocks. Some of them have been retained and maintained up to our times, and we see it now with the comet. So what about, how does it work? What is the process? How do you go from this cloud to the disk? So this is not obvious and it's not easy, so I will go very fast here. I don't want to bother you with all, I don't have the time anyway, with all the details of the physics, magnetohydrodynamics, but I just want you to tell you that you have the cloud with dust and gas, but that's not the only ingredient. As I mentioned, there is already cosmic rays, but most importantly, there is magnetic field that, of course, regulate the dynamical evolution. And one thing that we found with Bo Zhao, when he was with me at MPE, he ran non-ideal MHD. So this means taking into account magnetic field properly. We implemented a very simplified chemical code inside these non-ideal MHD simulations. And one thing that Bo realized is that it very much depends if there are small dust grains still in the gas phase, maintaining the gas phase or not. And what I mean by very small dust grains that I call here VSGs, between 10 and 100 angstrom, they are nothing else that these PAHs, so polycyclic aromatic hydrocarbons, that we see them everywhere in the universe, not just in our galaxy, okay? So these are these flat structured carbon and hydrogen molecules, large molecules, in fact, we could call them. So you can see, in fact, here that if we maintain very small grains in the gas phase, there is no way we can form a disk. If we eliminate these very small grains, we can form a disk. This has all to do with the relation between the charges and magnetic field. Very small grains are charged, they drag the magnetic field in, and if you have too much magnetic field, you basically lose angular momentum, you never form the protoplanetary disk. But without very small grains, you can actually form all this you want, just changing a little bit the initial conditions. So this is the face on view, and this is the edge on view. You can form this with spirals, with gaps, whatever you want. And the interesting thing is that what this means, I mean, so what does it mean that they disappear? Well, they are completely depleted, like CO and other molecules, in ices, okay? So you have to think that the large abundance of these PAHs must go into these ices. So your ices are not just composed by CO, water, CO2, methanol. You have these complex, organic, complex rings, okay? And this is what I think is going on to explain, for example, the insoluble organic matter that is found in the primitive material in our solar system. You see here lots of rings, very complex, with sulfur, with oxygen, with many, but I think that this is probably comes from the reprocessing of these pHs that have been incorporated in the ice. And this is something that, of course, would require a lot of experimental work to prove that, and hopefully we will be able to do it at some point. This is the soluble organic matter, by the way, that is also present in a little bit more reprocessed material in our solar system, still primitive material, and these are mainly amino acids. So the last few minutes, I want to just tell you about some important new results that come from observations. So we recently found that this is actually work led by Jaime Pineda, that is, although you are forming disks, and then of course planets will form, the connection between the stellar system that is forming and the mother cloud never ends. Because, for example, what Jaime found was that within this little region where the protoplanetary disk is actually already present, this is another very young stellar object, you have streamers of material coming from the cloud, bringing in chemically young material. By chemically young, I mean molecules that need a lot of carbon. So carbon is still in atomic form and not mainly locked in CO. So we have these chains of carbon brought in toward the protoplanetary disk that we need to take into account if we wanted to understand the chemical and dynamical evolution of these disks. In fact, the disks are complicated beasts with regions where we may have very thick ices and regions that are illuminated by the radiation from the central star. We have grain growth, a lot of processes going on. By the way, this is a Hubble Space Telescope view of a disk where you see edge on and you see the protostar in the center that is actually illuminating the dust. And you see this reddish light. And of course, ALMA has given us beautiful pictures of disks. This is a class 1, so a little bit more evolved disk that we see here, lots of rings that mostly have been carved, probably have been carved by young planets. And Dominique Segura-Cox, during her stay at MPE, she used ALMA to actually look at even younger disks to see if we have these rings and early phases of planet formation even in younger disks. And indeed, she found not well carved, as in the famous HL tau disk that was seen before. But even here, you can see actually some bumps and things that, in fact, may tell us that planet formation starts early. Okay, so the final thing that I want to say is that even in the later stages of planet formation, so in this case, for example, is almost a class 2 disk. So there is not anymore the core, the former prestellar core is gone at this point, has been completely, say, sent away by the outflow that these winds that come from the protostar. But you still see accretion of material from the larger molecular cloud. So you see here these streamers coming into this disk that is actually forming a planet at the moment. There is a big gap. This is now seen edge on. So you see the gap here. This is the protostar. This one of the, say, torus. And then there is a huge gap where a planet is forming. So this link with the mother cloud is always there, and we need to take into account. Last slide, sorry, the penultimate. Just to say, this is work by Karin Oberg, and there is much more work that please have a look in the literature. There is a huge amount of work done with the new MAPS large project with ALMA, where people have been detecting lots of molecules. But this work by Karin Oberg was particularly important because it told us that complex cyanide and have actually similar abundances compared to comets. So this relation between abundances of complex organics, or also organic molecules in general, and abundances in comets is persisting from star-forming region down to a protoplanetary disk. So as the end slide, I just want to conclude saying that with astrochemistry and our studies of, say, molecules in space, going from clouds to planets, basically, we can actually really try to make this link, dynamical and chemical links that take us from prestellar core to planetary systems like our own. And of course, the next step is the observation of exoplanet atmosphere, which has been already very rich. We know quite a lot, especially for the simple molecules. But now, of course, the future is very bright because we have the new instrumentation, and I would like to advertise the gravity receiver that is at the say VLT telescope here. So this is an interferometer type of observations that allow you to detect very so not in transmission, or you just go and point at your planet and you can detect, say, the composition of the atmosphere. And of course, there is Gravity Plus that will be even more sensitive, the extremely large telescope, the JWST that has been successfully launched, and we are all waiting to see the first images. And of course, we have Ariel and NGVLA and SKA in the future. So our field is really going to be very bright in the next decade, and we will definitely learn more. So thank you very much for listening, and sorry for being a bit late.
Okay, many thanks, Paola, for this very interesting lecture. As usual in our seminars, you can now ask questions.
Let me put like some kind of summary slide in case somebody wants to link to
Eva, yes. Okay, Eva, please, if you want to ask a question, please go ahead.
Yes, thank you, Paola, so much. I mean, I really enjoyed it. It was a great overview of so many exciting things. And you see, there's you touch very important point that we are all trying to put together the evolutionary stages from the molecular cloud to the mature planetary system. That is really very complex. And after what you said, I think, well, I don't want to be pessimistic. It's really very hard to go forward. But I mean, there are quite clever ideas how to go from one step to another. I mean, how the chemistry can evolve, and is it possible to just have initial conditions for the sort of short path of evolution from one step to another, and then to check with the observations if we are in the right track or not, and how far we can go with that? Could you comment on that?
Yeah. That's it. So first of all, hello, Eva. Thanks for being, for looking at my talk. No, this is a very important question, and it's actually basically at the beginning of our mission, say. So what we are doing now is indeed start with, say, molecular clouds. We can follow the chemistry during, say, the evolution of these clouds, making many assumptions, Eva. So I'm not saying that we understood all the details. For example, in our chemical models, where we actually model also more complex organic molecules, we assume that dust grains are spheres, and they have very simple surfaces, which of course is not the case, but we need to make this simplification if we want to have a complex, say, chemical network. So we can evolve this chemistry, this complex chemistry, typically in simplified, say, dynamical structures. So you can start with the spherical cloud, and collapse it, and look into the evolution of the chemistry, both in the gas phase and in the surface, and actually arrive at the formation of the protoplanetary disk. Now, once you arrive at this, so this is the same one side of, say, one group of people is working on that, so complex chemistry and simplified physics. On the other hand, we also look into the complex physics and simplified chemistry, and look into the details of how things really go if you take into account asymmetries, so your cloud is not spherical, you have magnetic fields and things like that. In that case, the chemistry is very simplified, but then you can check if what we are looking at are, have some similarities. For example, looking at the velocity field and looking at the temperature structure, looking at the structure of your cloud. And this is very important because the molecules being actually having a very well-known, very precise information about the frequency of your lines, you can actually measure the velocity field in much detail. So you have actually another constraint that from observation you can test your models. So it's not just the composition of your cloud, but also the kinematics of your cloud that you can actually test. Of course, the top aim of all of us is to have this chemistry put together into the complex dynamics, but we are not there yet.
Yeah, and especially when I sort of probably I never realized this, that I mean this connection after the formation of the protoplanetary disk, which I mean the cloud from which it's formed is always continuously, and this will make a complication, additional complication to the whole calculation, really.
Exactly. And I think what is one of the big challenges from my point of view that we need to be bold and start doing it is actually to study, once you are in the protoplanetary disk, is to study not just the grain growth, which is already a very complex physical process, but study the grain growth and the mineralogy of this dust, because you have dust and ice mixed together, growing together, and then you have this is, say, the precursors of what it will form, this complex prebiotic molecules that we see in primitive material in our solar system. And this is also important because it tells you, it gives you the true ingredients of the planets that you're forming. If you don't take this into account, you will never know which type of atmosphere your planet is going to have, especially for the terrestrial planets, because they are not going to accrete much of the gas from the protoplanetary disk like the giant planets. So it is really important, of course very difficult, because one needs to implement, so to have actually a geochemist, geophysicist in this very interdisciplinary field. So we need a chemist, we need an astronomer, we need a geochemist to actually follow all these steps, but it's very important. So you just arrived at the key point, the key question.
Thank you so much. I will keep trying.
Thank you, Eva.
Hi, Paola.
Hello.
Hi, this is Shubhadeep.
Hello, Shubhadeep. Nice to hear you.
Thank you for this wonderful presentation. I was just wondering, in one of your slides, you were talking about the interaction of pHs with the ices, and I was indeed very curious about that. So could you please comment a little bit more, like what kind of studies are possible to do to understand the formation of various prebiotic molecules? Yes, exactly, in the slides. So could you, yeah.
Well, I mean, so I know that some people have done some work on, unfortunately, you see, my memory is very bad. So I don't remember now the authors of the papers, but there have been people actually studying at least the spectroscopy of pHs embedded in ice. And I think this is very important because with JWST, we may be able to see these features, no? Because first of all, we have to prove that what we are saying is correct. It feels it is correct. This is not nice to say from a scientist, but the reason is that we see this very large depletion of everything. Every molecule is frozen, so why not these large molecules that are even heavier? So I think we will wait to see and prove. JWST hopefully will find these features. But I think that what is even more important, and probably some groups are already doing it, is to actually do chemistry with this. So you have your simple ice, your pH is embedded, and then you bombard it. No, you bombard it with some electrons, with some protons, and see what happens in the chemistry of your ice. Because I think you do not transform a pH into this, into this complex insoluble organic matter if you don't have some sort of irradiation. But we do have irradiation. We do have it from the interstellar medium, as we said, from cosmic rays, but also the sun itself and all the young stars have actually produced X-rays. They have this wind of energetic particles. So, you know, there is this irradiation. So it'd be nice to actually have some more quantitative work done in this side and see if you can arrive at structure that resemble these complex organic matter. Okay. So please do it.
Yeah. Okay, thank you.
You're welcome.
Any more questions and comments, please?
Yes, Jean-Luc Filion, I would have a question. Paola, thank you for this review. At some point, you mentioned the current understanding about the observation of comets in cold regions. So, could you come back on it a little bit? I mean, you mentioned something concerning the desorption of methanol, which that was more easy because of so rich surface. I
Yes.
didn't clearly have in mind
Yes.
what is behind. Could you comment?
Yes. Okay. No, this is, thank you very much. Yes, this is this is an important point. Maybe what I can do, if Wolf allow me, I just unshare a second and go to the slide, because otherwise I have extra slide, too many extra slides. So I need to, here it is. So now I share again my screen, and here, share and play. So this is the work from Vasiunin that I mentioned. This is the paper by Anton Vasiunin and collaborators. I'm also there, and is in there also François Douliou and Itasco Jimenez Serra. So in this paper, we included in the chemistry the, at that time, recent work by Minisale, Douliou, and collaborators on the reactive desorption efficiency of molecules depending on the composition of the surface on which they form. So this plot actually put in a diagram, say what the Minisale et al. Found. So this reactive desorption efficiency actually was found to be very sensitive to what is called the effective mass of surface element, that for water is about, say, at this level here. So here is like, 50 AMU, a little bit below. So it's not one single molecule. By effective mass of surface elements, it is like a structural element of the solid. And then this is the same value of this effective mass for the CO surface and CO only surface, and this is the bare grain. So you can see that the reactive efficiency, reactive desorption efficiency, so it means the efficiency of desorption upon formation of a molecule is very low if you have a water ice or water rich ice mantle. But it becomes very large, so of the order of, say, 10 to the -2 or 10 to the -1, depending if you're talking about here formaldehyde or methanol, if you have either a bare grain, but you don't have the bare grain in molecular clouds, because we know there is ice there, or if you have a CO-rich ice mantle, and we know that must be CO-rich, because you have this, what we call this catastrophic CO freeze out. So in these conditions, so once you, in your molecular cloud, you form a dense core and you start to catastrophically freeze out the CO, you have these thick ice mantles mainly made out of CO. They get hydrogenated quite efficiently, and once you get to the formaldehyde or the methanol, you have some desorption. You see, I mean, it's not so huge in the case of the methanol, but it's enough to explain the observations that we have of methanol in the gas phase. So it's all, say, experimental work. More work has been done more recently in Leiden. There is work by, I think, Lichtering and Chang. I don't remember now again. I'm so sorry. I'm so bad with the names. And that they have also looked at these and found very low desorption rate, but they are, say, consistent with this. So they have upper limits that are consistent with the work of Minisale. So this is what I mean by this importance of following the evolution of the chemical structure of icy mantles if we want to follow the chemistry. I hope it's clear, but otherwise,
yes.
I can also in the email.
Very clear. Yes, thank you.
Okay, thank you.
Any other questions? Seems not to be the case. Well, If that is not really the case, then I will thank Paola again, and I invite you for the next seminar, which will be by Ben Pierce on the 1st of February. So I hope to see you then again and wish you a nice evening.
Thank you.